Srimati R. Padmavati, Head of Department ECE, Dhanalakshmi Srinivasan College of Engineering and Technology, Chennai. She pursued her Bachelor of Engineering in Electronics and Instrumentation Engineering at the National Engineering College, Kovilpatti. She then went on to work as a technical editor in Domix Technical Information Private Limited, Chennai. She then pursued her Masters of Engineering in Applied Electronics at the Satyabama University, Chennai. She is currently pursuing her PhD in Anna University, Chennai. She has published several national and international journals and has attended many conferences. Her areas of interest include linear integrated circuits, digital electronics, electronic circuits, VLSI design.
Welcome to UGC lecture series BSc Applied Electronics, the subject oscillators and amplifiers, in which we are going to see about the amplifiers, two-port network, Z parameter, Y parameter, H parameter, small hybrid model of two-port network and small signal analysis of transistor. So, when you see the block diagram, it is representing the two-port network. Here this is the input port or port 1, and here this is the output port or port 2, and the input current is represented by I1 and input voltage is represented by V1, and here the output current is represented by I2 and output voltage is represented by V2. So, here this is the input port and this is the output port. So, there are two ports, so it is a two-port network. Here the behavior of the transistor can be studied by various parameters such as Z parameter, Y parameter and H parameter. Z parameter is otherwise called as impedance parameter, Y parameter is admittance parameter and H is hybrid parameter. And this Z parameter, how will you write this equation, or how you calculate this Z parameters? By the variables of the two-port network. What are the variables? We have seen it is I1, V1 and I2, V2. I1, I2 are the input output currents and V1, V2 are the input output voltages. From these variables we can define or we can calculate all these Z parameters. So, to calculate the Z parameter, when you see the equation of the voltage and the current, here this is represented for H parameters. If it is for Z parameter, we have to consider two variables as independent variable and the other two variables are the function of those independent variables. For Z parameter, the input current and the output current are considered to be the independent variables, and the input and output voltage are considered as dependent variables, or they are written as the function of those independent variables. Here this is for the hybrid parameter, we have written it. For example, if it is for Z parameter, how it will be, the equation will be. So, as I said, the two voltages V1 and V2 are considered to be the dependent variables of the current I1 and I2, and those I1 and I2 currents are independent variables. So, here instead of this VB, you have to write it as V1 equal to Z11 and here I1 plus Z12 I2, that is the equation for V1, and for V2 here Z21, instead of this IB you have to write it as I1 plus Z22, this is V2. So, this is the equation for the Z parameter. So, from those equation, the parameter Z11, Z22, Z12 and Z21 are calculated by V1 by I1 with the I2 equal to 0. So, if I2 is 0 means the output port must be open circuited. So, the input impedance with output port open circuited, and similarly Z22, from that equation Z22 is written as V2 by I2 with I1 0, I1 0 in the sense the input port must be open circuited, and this Z11 is said to be input impedance, Z22 is said to be output impedance. And what is Z12 and Z21? Z12 is reverse transfer impedance and Z21 is the forward transfer impedance. So, here From the equation we have written Z12 reversed impedance is calculated as V1 by I2 with I1 equal to 0. So, the input port is open circuited. Here the forward transfer impedance with port 2 open circuited, it is given as V2 by I1 with I2 equal to 0. So, in this way you have to calculate the Z parameters of the two port network, and Y parameter similarly we have considered the two variables I1 and I2 as independent variable, and V1 and V2 are the function of I1 and I2 for Z parameter. Now, the admittance, for the admittance parameter, it has to be reversed. I1 and I2 are the dependent variables or the function of V1 and V2. V1 and V2 are the independent variables here. So, how will you write the equation? If you want to write the equation for y11, not here, y11 will be given as I1 by V1 with V2 equal to 0. How you will be getting this equation for y11? So, as I said, the input and output voltages are independent, and input and output current are the function of these two voltages. So, how will you write the equation for I1? I1 is equal to y11 into V1 plus y12 into V2. This is the equation for I1, and for I2, I2 is equal to y21 V1 plus y22 V2. This is the equation for I2. So, from this equation you got all the parameters of y here. Y11 is there, y12 and y21 and 22 all are there in these two equations, I1 and I2. So, I1 and I2 is the function of V1 and V2. I1, I2 are the input output currents, and V1, V2 are the input output voltages. So, from these two equations you are going to derive all the admittance parameters y11, y22, y12 and y21. So, if you consider V2 as 0, if current is 0, then it has to be considered as open circuit, and if voltage is 0, it has to be considered as short circuit, right. So, y11 is given as I1 by V1 with V2 equal to 0. So, from the two equations we have considered for I1 and I2, from those two equations you are getting all these parameters, one variable as 0. So, here if you want to calculate y11, you make V2 as 0. If V2 is 0, in the sense the output port is short circuited. You all know that whenever there is an open circuit, the voltage is maximum, and if it is short circuit, the voltage is 0. Similarly, for the current, whenever there is a short circuit, the current is maximum, and if there is an open circuit, then the current is 0. So, whenever you got the voltages are considered as 0, the port, that particular port is considered as short circuited. So, y11 is the input impedance with port 2 short circuited, and y22 is the output admittance with the port 1 short circuited, and this is reverse transfer admittance and forward transfer admittance parameter, which is again calculated from the same equation with V1 equal to 0. So, this is input port short circuited, and here output port V2 is 0, output port is short circuited. So, in this way you have calculated all the admittances, and here the next is H parameters. So, there is an importance in this H parameter when you compare with the other two parameters. You know that Z is represented for the impedance and Y is represented for the admittance, and H is represented for hybrid. What do you mean by hybrid? Hybrid is a collection of different categories. Here H11 says that it is input impedance, and H22 is output admittance, H12 is reverse voltage transfer ratio, it is nothing but voltage gain, reverse voltage gain, and H21 is forward current gain. So, in previous parameters you have calculated only the input impedance, output impedance, and the reverse input impedance and forward output impedance, and in similarly for the admittance parameters also. Here in H parameter you can calculate the input impedance, output admittance and reverse voltage transfer ratio, forward current transfer ratio. So, there are 4 parameters and 4 are different, and so it is called as hybrid parameter. How will you calculate these parameters? Again, here the equation for this hybrid parameter is given as input voltage for any circuit, for any transistor model, input voltage and output current is the function of the other 2 parameters. When you look at this equation, VB is the input voltage according to the common emitter configuration, VB is the input voltage and IC is the output current. So, these are the equations given for VB and IC. So, input voltage is taken as the function of the other 2 parameter. The other parameters are IB and VC. What is this IB and VC? When you see circuit common emitter configuration, this IB is the input current and VC is the output voltage. So, in the 2-port network we have seen that 2 parameters are independent and other 2 parameters are the function of those 2 parameters, and the input current, input voltage, output current and output voltage are the parameters, and here VB and IC are the dependent parameters and IB and VC are the independent parameters. So, with this independent parameters, the other 2 parameters have been written. So, in this way the hybrid parameters are calculated. So, here VB is written as HIE into IB plus HRE into VC. So, HIE is the input impedance for the emitter configuration, that is E is for the emitter configuration and HI is the input impedance, and HRE is the reverse voltage transfer ratio. Here HFE is forward current transfer ratio and HOE is output admittance, and here in all the H parameter E is represented for emitter configuration. When you see this for the collector or common base configuration, this is for common base. This common base configuration, everywhere for the hybrid parameter you will be seeing the B in suffix, and for common collector it is C, instead of B it is C. So, HIC, HRC, HFC and HOC. The second parameter in the suffix represents the common terminal in the configuration, and from the equation written for those 2 variables you can calculate the parameters in H. So, this input impedance is calculated as VB by IB with VC equal to 0. So, with VC equal to 0, in the sense VC is the output voltage. So, output voltage, if it is 0, then the output port must be short circuited. So, with the output port short circuited, the HIE is calculated as VB by IB. Similarly, wherever VC is taken as 0, the output port is short circuited, and here IB, if IB is taken as 0, then the input port is open circuited. With this assumption, all the parameters are calculated based on those 2 equations written for the dependent variables, and here this is the hybrid model for common emitter, common base and common collector configuration of the transistor. So, here in this diagram, when you look at this common emitter configuration, see here the hybrid model is given as HIE in series with the voltage source. This is a voltage source, and HOE in shunt with the current source. So, you have to say that the input side of the transistor is equivalently given in a Thevenin equivalent circuit, and output part of the transistor is given in Norton equivalent circuit. So, we know that for the Thevenin equivalent circuit, the source is in series with the resistance, and in Norton circuit the source, the current source should be parallel with the resistance. So, that is the concept. This transistor is a two-port network. We know that one of the terminal is common for the input and the output. So, this is the two-port network, and this transistor is equivalently given in H model as the Thevenin equivalent circuit in the input side and Norton equivalent circuit in the output side. And for this we have given the equation. Similarly, for common base we know you have to change the input and output terminal and also the common terminal according to the configuration. So, here the input terminal is base and common terminal is emitter, output terminal is collector. So, when you see the hybrid parameter, the hybrid model, input terminal is B, output terminal is C and common terminal is emitter. Let us have a break. Welcome back. So, we have seen the hybrid equivalent circuit for common emitter. When you look at this common base configuration, common base transistor, emitter is the input terminal, collector is the output terminal and base is the common terminal. Similarly, here when you see the hybrid circuit, hybrid equivalent circuit, this base is common and emitter is the input and collector is the output. So, you have to change the terminals according to the configuration of the transistor. And C common collector, you know that the base is the input, output is emitter, across the emitter you have to take the output and collector is common. So, common terminal you can mention as C and base is input and emitter is output. So, everything was corrected according to the configuration of the transistor. So, this is the hybrid model for all the configuration of transistor. And next we have seen the hybrid equivalent circuit only for the transistor model, and if this transistor is signaled, if this transistor is given the supply and connected with the load, then this is the circuit. This block diagram shows that the transistor is given with the source and connected with the resistance at the output, impedance at the output, and this is the source resistance, and input voltage is V1, current is I1, output voltage is V2 and current is I2, and this is the input port and this is the output port. 1 dash shows the input port, 2 dash shows the output port, and if you look at this input side, you can calculate the input impedance parameter, and when you look at this output side towards the transistor, you can calculate the output admittance of the circuit. Transistor replaced by its hybrid model. So, here this is the transistor, two port active network, that is the transistor, and transistor's hybrid model is this. When you use the common emitter configuration, this is the hybrid model. So, instead of this transistor, you have to use this hybrid model in the circuit. So, consider this is a transistor in common emitter. We have replaced the hybrid model for the transistor part, and beyond this hybrid model, you can see the resistance of source and also the voltage source here, and at the output there is a impedance connected. So, this is what we have seen in the block also, in this diagram also. Only thing, this two port active network is replaced with the hybrid circuit here. We know that the hybrid circuit consists HI, that is the input impedance, the reverse voltage transfer ratio at the input side, and at the output side the forward current transfer ratio is there and the output admittance. So, all the parameters are given here. Hi in series with the voltage source, H0 in shunt with the current source here, and this is the entire circuit. For this circuit, we have to analyze in the small signal analysis mode, and you have to derive all the parameters. What are the parameters? Input impedance, output admittance, the current gain and the voltage gain. First, the current gain. Current gain, we know that the output current by the input current. Output current is IL and the input current is I1. So, IL by I1, and when you see the polarity for this load current IL, this is reversed with this I2, and I2 and IL equal in magnitude, but in differ in polarity. So, it is reversed. So, instead of this IL you can replace with minus I2 in the equation. So, it is minus I2 by I1. And what is I2? I2 is the current flowing through this resistance. This can be written as HF I1 plus H naught V2. So, this is going to flow this part and here through this resistance also, admittance also. So, this I2 can be written as, this is the current source. So, you can straight away give as HF I1 plus this current, this I2 is splitted here. So, this current plus the current flowing through this admittance. So, H naught V2 you can write it. And what is V2? V2 is the output voltage, that is the voltage across the output terminals. Output terminals voltage is written as minus I2 ZL, because IL ZL is the output voltage. If IL is replaced by minus I2, then V2 can be written as minus I2 ZL. This V2 is substituted in the I2 equation, and this is taken to the left hand side, and I2 is taken common, and AI can be written as minus I2 by I1 is equal to minus HF by 1 plus H naught ZL. Here there is no another alphabet in the suffix, only you have only one alphabet referring the parameter forward or forward current transfer ratio or the output admittance and so. Why there is no alphabet for representing the configuration is, we are talking about in general transistor. For any transistor, this is the way you have to calculate the gain or whatever it may be. And if it is a common emitter transistor, you have to include E here. Wherever the H parameter is there, you have to include E at the suffix. So, we have calculated the current gain as minus HF by 1 plus H naught ZL, where HF is the forward current transfer ratio and H naught is the output admittance. ZL is the load impedance. Next is input impedance. Input impedance, when you look at the input port in the circuit, it is given as V1 by I1. How can you write this V1 equation? V1 is the voltage at the input side. When you see this circuit, V1 can be written as the voltage drop across this resistance and also this voltage. So, this is given as I1 HI plus HR V2, that is the voltage. If you substitute this V1 in this ZI equation, will be like this by I1, and I1 cancelled out here in the first term, and here you are having again V2. We have calculated V2 as minus I2 ZL. So, replace this minus I2 ZL here, and minus I2 again can be written as AI I1, because AI is the current amplification factor, can be written as minus I2 by I1. So, minus I2 can be taken as AI I1 ZL. This term is substituted here and you are getting AI I1 ZL by I1 into HR for the second term, and again I1 get cancelled, and the final input impedance is this HI plus HRAI ZL. Substituting for AI again, AI is the first derivation we have calculated, this one AI, the current amplification factor. So, this is substituted in the ZI equation here, and after substituting the value, you are taking out the ZL term, and so you will be having 1 by ZL in the denominator, and this can be written as YL, that is the admittance. And input impedance, after simplifying this, the input impedance will be written in terms of output admittance here, YL, and it is inversely proposed. And next is voltage gain. Voltage gain, we know that it can be given as the output voltage by the input voltage, and what is output? It is V2 by V1, and we know that what is V2? It is minus I2 into ZL, and it is again AI I1 ZL. So, the voltage gain can be written as substitute the V2 here. I1 and V1 can be replaced by 1 by Zi. So, it is given like this. So, this is the voltage gain without the source. So, here the voltage gain is calculated with Vs is equal to 0. We are assuming that the source voltage is 0 here. Only the voltage, input voltage of the port and the output voltage of the port, that is the consideration here. Output admittance Y0 is calculated as Y0 is I2 by V2, and I2 is written, we have taken from the circuit as HF I1 plus H0 V2 initially, and this was substituted here. V2 is cancelled out. With Vs equal to 0 and applying KVL in the input circuit, you will be getting this equation. So, when you look at the input side of the equation, this is the input side of the equation, apply KVL here. This is the voltage drop, the KVL is the source minus the voltage drop across all the resistances equal to 0. So, by this KVL, Kirchhoff's voltage law, you are calculating Rs I1 plus Hi I1 plus Hr V2 equal to 0, and that is we are assuming the voltage source equal to 0 here. That is what you are getting. That is only the drop across the resistances we have considered here, that is equated to 0. And from this I1 is taken out, and here I1 by V2 can be calculated, and you can substitute in this equation I2 by V2. So, after substituting, you are getting the output admittance as H0 minus HF HR by Hi plus Rs, and these are all the equations for the voltage amplification with the voltage source resistance. With the source resistance, in the sense you have to assume input side of the circuit as Thevenin equivalent circuit. So, you will be getting AV V1 by Vs. We know that for the Thevenin equivalent circuit, the resistance must be connected in series with the source. That is what you have considered here. From this circuit, you are calculating the voltage across the impedance Zi as Vs into Zi divided by the total resistance, after which you are substituting the values of V1 to calculate this AVS, that is with the source, the current voltage amplification factor with the source resistance, and this is the current amplification factor with the source resistance. Previously we have calculated the voltage gain and the current gain without this source resistance. Now it is with the source resistance. Current amplification factor, we are considering the input part as Norton's equivalent circuit, and you know that for the Norton's equivalent circuit, the current source is connected in series with the source resistance, and from here you are calculating the current through the resistance Zi as the source current into the opposite resistance divided by the total resistance. So, from which after substituting the values of I1 in the overall voltage gain, you will be getting AI into Rs by Rs plus Zi, and this is the formula or equations we have derived from the hybrid equivalent circuit of the general transistor model, and this is exact common emitter hybrid model. So, when you look at the circuit diagram, this is CE is nothing but the common emitter model. So, everywhere H parameter is present, everywhere the suffix E is present, and also the source is connected and through the resistance, and here the load resistance is also connected. So, transistor is replaced with the hybrid model, and to the transistor we have given the source and we have connected the load resistance also. And this is the approximate common emitter hybrid model. And what is the difference between the exact hybrid model and the approximate model is, when you look at the circuit, you can easily say that there are 4 parameters in the exact hybrid model. 4 parameters are HIE, HRE, HFE and HOE. And when you look at the approximate model, you will not find out HRE and HOE. It is only HIE and HFE. What happened to this HRE and HOE is, this value HRE as well as HOE is very negligible. So, you are considering only the input impedance and the forward current transfer ratio. These 2 parameters are neglected in the approximate model. That is what you have included, only the input impedance and the forward current transfer ratio in this model. And this is the approximate H model for common emitter, common base and common collector configuration. So, whatever may be the input terminal and whatever may be the output terminal or a common terminal, this is the approximate model. You have to connect the source to the input terminal and the load to the output terminal. Let us summarize what we have seen today. We have seen what is a two-port network and what are the parameters to study the behavior of the two-port network, and the parameters are Z, Y and H. And out of these three parameters, how the H parameters differ we have seen, and hybrid model of the transistor circuit, exact model and approximate model, small signal analysis of the transistor amplifier circuit using hybrid model. Small signal analysis in the sense we have calculated all the parameters for a general transistor with the hybrid model. Can you answer for these questions? Why H parameter is called so? List the two-port parameters used to study the behavior of an amplifier. Derive the H parameters for a two-port network. This is the reference I have taken. Thank you.